Have you ever stopped to think about all the invisible forces at play in our workplaces? And no, I'm not talking about ghosts, but something that can be just as harmful, vibration. Today, we're going to unpack the really cool technology that makes this invisible force totally visible, and more importantly, measurable. We're diving into the clever science behind it all, and we'll start with why this is so critical in the first place. So yeah, why do we even need to measure vibration? Well, for a ton of workers out there, that constant shaking from tools and machinery isn't just a minor annoyance, it's a serious health hazard. Over time, all that exposure can lead to some really nasty health problems. So to protect people, we first have to understand the risk we're dealing with.
And check out this great illustration. It shows exactly where these vibrations come from. We're talking about everything from the power tools you hold in your hand. That's what causes something called hand-arm vibration, or HAV for short. And then you've got the big stuff, entire vehicles, industrial platforms. That's what causes whole body vibration, or what the pros call WBV. These are the things creating that constant physical stress.
That really is the million-dollar question, isn't it? A little bit of shaking is one thing, but how do we actually put a number on it? How do we know when we've crossed that line from what's okay to what's dangerous? Well, to answer that, you need a very special kind of tool.
And here it is. Meet the piezoelectric accelerometer. It might look small, but this little sensor is an absolute powerhouse. It's the key to measuring all those forces from vibration and turning them into something we can actually analyze.
At its heart, that's all this thing does. It sits there and experiences the very same shaking as the worker or the tool it's attached to, and then, through a really clever bit of physics, it converts that motion into a clear electrical signal we can read. So, how does it actually do that? Let's take a look inside.
All right, we are officially popping the hood on this thing. The process is surprisingly elegant and simple once you see the pieces. It all boils down to two critical parts working together in perfect harmony.
Okay, so everything hinges on these two parts. First, you've got the seismic mass. Now, just imagine you're holding a really heavy bowling ball. If someone suddenly shakes you, what's the bowling ball going to do? Right, it's going to want to stay put because of its inertia. Well, the seismic mass acts exactly like that bowling ball. And pressed right up against it is our second component, the real star of the show, the piezoelectric crystal.
So here's how it all comes together. First, the vibration from a tool shakes the entire body of the accelerometer. But, just like we said, that heavy seismic mass inside resists the movement. It wants to stay still. As it resists, it pushes down and actually compresses the piezoelectrical crystal. And this, right here, is where the magic happens. As that crystal gets squeezed, it generates an electrical charge that is perfectly proportional to the force of that vibration.
Now that magic I keep talking about, it actually has a name, the piezoelectric effect. This is the fundamental scientific principle that makes this whole thing possible. It's just a fascinating, almost unbelievable property that certain materials have.
It honestly sounds like something out of science fiction, right? You take a special type of crystal, you apply some mechanical pressure, literally just squeeze it, and boom, it spits out an electrical voltage. So what in the world is going on inside that material?
And here's the official definition for you. The piezoelectric effect is simply the ability of certain materials, like quartz, to generate an electric charge when you put them under mechanical stress. The word itself is pretty cool. It comes from the Greek word piezein, which literally means to squeeze or press.
Now, what's really cool is how this visualizes the effect. When that seismic mass squeezes the crystal, it basically deforms the crystal's internal structure, and that tiny change forces all the positive and negative charges inside to separate and run to opposite sides. This separation of charge is what creates a voltage that we can measure. So more vibration means more force, which means a bigger voltage. It's simple, it's direct, and it's incredibly effective.
Okay, so we've got this tiny little electrical charge coming from a crystal. That's neat, but how do we get from that to actually keeping a worker safe? This is where we zoom back out and connect that amazing science to its real-world purpose, occupational safety.
That raw electrical signal, it's not super useful by itself. It has to be processed and translated into data that a safety professional can actually look at and understand. So let's see what those key outputs are. That signal gets analyzed to give us three crucial pieces of information. First up is RMS acceleration. You can basically think of this as the overall intensity or power of the vibration. Then there's the frequency content. This tells us what kind of vibration is happening. Is it a slow rumble or a high-pitched buzz? And that matters because different frequencies affect our bodies in different ways.
And finally, you get the time history signal, which shows you exactly how that vibration changed from 1 second to the next.
And this right here is the ultimate payoff. All those outputs together paint a complete picture. They transform that invisible, potentially dangerous force into clear information you can actually do something with. Safety managers can use this data to see if exposure levels are too high, to pick safer tools, or to set up better work schedules, all with the single goal of preventing injuries.
So the next time you see a power tool or some heavy machinery, you'll know there's this incredible little sensor that might be working hard to keep the operator safe. It kind of makes you wonder, doesn't it? What other invisible forces are out there shaping our world, just waiting for the right tool and the right principle to finally make them seen?